Hello again, everybody, and welcome to another Geo-Institute live stream. It is the final week of July, and you have made it. We are getting perilously close to the end of summer, which seems unbelievable, but that is the state in which we find ourselves. And as such, Geo-Extreme is hurtling towards you at speeds that you cannot even process in your mind. July. My name is Brad Keeler. We are getting perilously close to the end of summer, which seems unbelievable, but sneak preview number 1. If you don't know anything about the Geo-Institute, after you watch this today, well, you're going to know more already, but you can then proceed on to geoinstitute.org, and there you will find out a bunch more stuff, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that, yes, we are part of the American Society of Civil Engineers. A very important thing that I would urge you all to do is click like, subscribe, and get notifications. And if you do those things, you should do them in that order. We will let you know every time we post something to the YouTube channel. The matter at hand today is, yes, Geo-Extreme is coming. If you don't know anything about Geo-Extreme, we have somebody here from the conference committee who's going to tell you something about that in a minute. But what you should do first and foremost is head over to geo-extreme. Yes, there is a hyphen in that address, .org. And you can find out all kinds of info about the conference, the location, the exhibitor floor plan. If you'd like to purchase an exhibit booth or a sponsorship, you can do so. You can look at the program details over here. You can look at these beautiful images, some of which were taken by our program committee. And most importantly, as of Friday, you can click this registration link and go get information about registration and actually register yourself to attend the event in Long Beach in November. So, with all that out of the way, I mentioned that we have a real live member of the program committee here today. And he's here to tell you a little bit more about the program today and also urge you to go to the conference. From Texas A&M University, where he is a faculty member, it is Naveed Jafari. Naveed, thank you. Welcome for doing this.
Thank you, Brad. Thank you for having me. And thank you for letting me moderate this session. I'm really excited. This is our first live stream for our upcoming Geo-Extreme 2025 conference. I'm a co-chair with Daniel Purdell from the Ohio State University. We're making our preparations for the conference. We've got all the technical sessions laid out. We're outlining our keynote lectures and our themes, and they range everything from wildfires to landslides to reconnaissance and seismic or earthquake engineering. It's going to be very exciting. We have a lot that we're going to offer. And I recommend you to go to the Geo-Extreme website, register, and go ahead and get that out of the way while you can. So with that, I'd like to introduce 2 speakers. This is our first live stream to kind of highlight the conference. So our 2 speakers are Pavlo and Taki Chrysovergis, and they're going to be presenting some of their work related to wildfires. Now, let me do a quick intro on both of our speakers today. Taki Chrysovergis is a principal engineer at SPC Engineering. He's licensed as a geotechnical in California, along with 5 Western states, and I think that includes Texas. He manages various geotechnical and civil engineering projects that are both public and private, along with forensic analyses. Taki regularly performs geotechnical investigations related to failure and construction claims. And in addition to his professional work, and this is what I think is very, very important, he gives back. Taki has been an adjunct lecturer at UC Irvine and Cal State Long Beach. He graduated with a bachelor's and master's in civil engineering from Cal Poly San Luis Obispo with an emphasis in geotechnical engineering, and is currently a PhD candidate at UC Irvine. So very, very fascinating. Pavlo is also a principal engineer at SPC Engineering, where he manages design construction projects similar to Taki. He's also heavily involved with forensic matters investigations. And more differently, I guess, is Pavlo also oversees the drone and LiDAR operations at SPC. So that's quite impressive. Pavlo also holds a bachelor's and master's in civil and environmental engineering and geotechnical engineering from University of California, Los Angeles. He's a registered geotechnical engineer in California, and I think he's beat his brother by having one more state. He's got 6 states. He's an FAA licensed drone pilot. So with that, they're going to present some recent work, relatively recent work. Some of it is covered in a paper that will be in Geo-Extreme 2025. It's co-authored by their father, Stavros Chrysovergis, and the 2 brothers, and it's titled Methodologies for Effective Slope Failure Reconnaissance. With that, Taki and Pavlo, thank you for coming and presenting for us, and I'm going to hand over the reins to you so you can present.
Thanks for the very, very kind introduction, Naveed. Let's see. Okay, can you see the presentation full, the full slide?
Yes.
Okay, very good. And so when Brad first approached us about doing a presentation, for those of you, I think most of you are aware, is that in 2025, in January, we had some devastating wildfires in Southern California, 2 of them. They were covered huge areas, of unprecedented size in these urban areas. And so we thought that this topic about post-wildfire erosional and flooding damage would be very applicable. So, because it's a current topic, and also it's a great case history. So, to create lessons learned. So did some introductions earlier. We've both been past chairs of the Orange County Geo-Institute chapter, and that's been a great experience. One more thing I wanted to say about the Geo-Extreme is that, I did attend in 2019. I thought it was an excellent conference. And so I highly recommend everyone to attend from all over the country. And you cannot find a conference with a closer airport than at Long Beach. So that would be another bonus to attending. So this is our company, SPC Engineering. We do design and construction services, and we do emphasize in forensic engineering. We were established in 1990 by our parents, Stavros and Helen, and today happens to be our father's 75th birthday. So happy birthday to our dad, who's watching. And we're based in Anaheim, and we serve a variety of West Coast and Southwest states.
All right, so regarding the site for this presentation here, it's located in Lake Elsinore, which is actually the largest natural freshwater lake in Southern California, believe it or not. It's located about an hour and a half southeast of Los Angeles, or about an hour and 15 minutes away from Long Beach, the future site where hopefully many of you will be at in a few months for Geo-Extreme. The site is located along the foothills of the Santa Ana Mountains along the east side. And as we will discuss in this presentation, there were wildfires in 2017 and 2018, followed by a storm event in February 2019, about 6 months later, that induced some debris flows.
So this is a 3D view, if you will, of the vicinity of the area that we're focusing on. So you can see there's a floodway at the bottom with that arrow. And then the yellow outline is roughly the watershed limits for this floodway. And there's 2 main canyons that feed this floodway. There's the Leech Canyon, which is on the right, and then there's Dickey Canyon on the left, and they combine to about 1,600 acres. And just note that you have the flow lines of the canyons, and then there are a lot of side canyons, and both of these main canyons have very similar terrain with these side canyons that go up at quite steep inclinations. And then that's where all the drainage, tributary area comes from that goes this floodway. This is a look at the geology. This is in blue is the watershed limits. And basically we have 2 main rock types that the canyons are made out of. There's the Jurassic metamorphic rocks, and then there's also Cretaceous granitic rocks, and of course you have alluvium in the bottom of the canyons. And just note, just going back to the previous images, anywhere where these side canyons are and these draws that come up, there's an accumulation of colluvium and alluvium inside of those side canyons that ultimately are prime candidates on those steep slopes to being part of the debris flows.
So Taki talked about the geology. Now going into the infrastructure and really the layout of the site, we mentioned the Leech Canyon Dam. So that dam is a smaller earthen dam, about a little less than 4 million cubic feet capacity, located at the base of the Leech Canyon. And you note that there is a concrete spillway along the left side of the photograph, the south end of the dam over here. So downstream of the dam, you have your floodway, and downstream of the dam and the spillway, you have your floodway, and basically the runoff or debris would flow through this triple box culvert and flow down through this this floodway channel, which is about 200 feet wide from end to end. How it was designed and intended. We'll get into the improvements that were, or rather the modifications that were performed along this floodway later in this presentation. But it was 200 feet wide and was designed for a 100-year design storm. Now we talked about the layout of the site. Now moving on to the wildfires that actually occurred in 2017 and 2018, the Rose and Holy Fires, respectively. They burned around 23,000 acres of mountainside, including all those canyons that Taki was showing, and about 97% of the Leech Canyon watershed was burned. So to put that into a visual context here are some satellite photographs. The left side is in February 2018, before the Holy Fire, and here's about August 2018. That was actually taken during the Holy Fire. You can actually see some of the extent of the fires along these edges here, this burnt perimeter. But within here, you can see the ash that's been deposited and basically the lack of vegetation, the denuded slopes along these Santa Ana Mountains over here.
And just one thing to note with the pictures Pablo's showing here is look at the locations of the homes, of the residential properties that are at the base of these canyons. So when we think about not only stormwater coming down, but also debris flows, obviously life safety is the number one importance for this kind of situation.
Exactly. But Tyke's going to talk now about the mechanisms of post-wildfire debris flows.
So I put together a slide here of just debris flows in general and why it matters. Sometimes their slope failures are, say, slow-moving slides, and even if they may cause property damage, there's enough time and warning. So for people to evacuate or for modifications to be made to improve the stability. But a lot of times with debris flows that are triggered by heavy rainfall and weak, steep slopes, they occur with no warning. And the velocities of the debris coming down can be very high because it's so steep, and the mass can be fluidized with entrained rocks and soil and all different kinds of debris in there. And that results in a bulk unit weight that can be almost double of just water unit weight. So that material is highly erosive, it can cause more damage. And so if you think about a steep slope where the debris flow originates, and at some point that slope flattens out, then all that entrained debris starts coming out of the entrained mass fluid, and it drops out. And when that material drops out, that can affect the way that drainage devices and improvements and facilities perform. Because if you have drainage facilities for water, that's one thing to handle a certain size storm. But when you start adding other types of debris in there, that can completely, affect the way the performance of that drainage improvement is. And then also just debris flows, because of their fluidized, they can travel very long distances, a lot further than, say, just an earthen failure. Now let's shift to debris flows that occur after wildfires. So there's a little graphic on the right that shows the vegetation being burned and an ash layer deposited. And there's a few factors that come into play after a wildfire occurs as far as considerations for evaluating debris flows and the possibility of them. So one is the increased raindrop erosion. So when there's vegetation before a wildfire, the vegetation provides some ground cover and reduces the velocity of the raindrops coming down and protects it. And then also the vegetation, the roots that the vegetation have that hold in the ground and help provide some superficial stability. If those are burned off, then now there's voids in there. It increases rodent activity. There's also the roots that are now gone. They're not helping hold up the surface of the soil, so you can get additional instability from there. The ash layer that's a result of the burned vegetation has a low shear strength, much lower than the native soil itself, and that can result in increased velocity of the debris that comes down. And so not only is the wildfire more likely to result in debris flows, but it also can increase the volume of the debris that comes down because of the wildfire, because of these things we talked about. Let's see. Yeah, that's it for this slide.
Now, Taki mentioned kind of the theory behind the debris flows, and especially that are wildfire induced in a way. Here are some brief case histories, taking it aside here just to look at various damages that are caused by debris flows. The one on the left side over here was basically due to a debris flow that caused rerouting of the original drainage channel. And basically this structure here was off the foothills, and then just a deluge of debris, rocks, and cobbles built up and was deposited right up against this house, about 9 feet of, or 9 or 10 feet of debris that built up here. Luckily, the house had a concrete foundation, so believe it or not, the damage was minimal, so to speak. And then on the right side over here, this was due to another debris flow. That there was initially a small creek that ran along here, but due to the large amount of mass and the bulk unit weight of the debris that flowed down this creek, it wiped out this whole stretch of road here. There's also, unfortunately, some other residences that were mobile homes that were further down the creek that also got washed away and displaced a few hundred yards. Here's another example of debris flows. This was a post-wildfire debris flow. You can see a lot of the organics that were deposited along the interior floor here. What happened is that this site was located adjacent to a creek outside of a flood zone, but the debris flow just went straight through the front door and then also exited from the rear. So just went straight through, caused a lot of damage. And coincidentally, afterwards, the area was rezoned from a flooding perspective.
All right, Taki. So going back to the area near Lake Elsinore, the case history we're going over is after the wildfire occurred, but before the rainy season. And in Southern California, we basically have a hot season during the hot, dry season during the summer season, and then the rain typically occurs between mostly November and February is most of our rain. And so between the fire that occurred in 2018 and then the 2019 rainy period, the U.S. Forestry Service did some evaluation for the potential for debris flows on those Santa Ana Mountains where the Holy Fire and the Rose Fire occurred in the previous 2 years. And they utilized modeling by USGS. And that model basically uses a series of geospatial data for the burn area to evaluate the probability of debris flows and the potential volume of debris flows as a response to a specific design storm. That's essentially how the model works. And what the modeling predicted was a 60 to 100% probability of debris flows for the design storm, which is over a 15-minute increment, 1 inch per hour rainfall rate. And the input parameters for the geospatial data includes the topography. Obviously, the steeper the topography, the more probable is debris flows to occur, burn severity, soil properties, and then rainfall characteristics. And so I'll be showing you some maps in a bit about how the results of this model for different types of outputs. Another thing too is that the estimated 10 to 100 cubic meters of debris volume for the watershed area we talked about, for that area before, this is of course before the rainy season started. And so here's one of the outputs for the soil burn severity. This is actually be for the inputs. So you can see this is a watershed area, and then moderate is yellow, high burn severity is red. And so you can see most of this area had moderate burn severity with isolated pockets of high burn severity. Now here are some of the outputs. This is for the probability of debris flows, and this is the watershed area in blue. You can see the red lines are the flow lines that have 60 to 80% probability of debris flows for the design storm. And then the black lines have 80 to 100% probability of debris flows for the design storm. And you can see most of these flow lines are 60 to 100% probability of debris flows. And you can look at the rest of the map as well, and there's some areas that are even higher probability. And then here is an estimate for the volume, the predicted volume of the debris flows. And this orange line over here is over 100,000 cubic meters, or about 130 cubic yards, 100,000 of cubic yards. And then this is a metric that they have as part of this model, which is the debris flow combined hazard. And essentially it combines the probability of debris flow with the estimated volume of debris flow, and it combines them into a single parameter. Now, there's no numbers with this, so maybe they could have like a 100 to 0 scale or something, but the red is high, this gold color is moderate, and you can see that the areas that have high hazard for debris flows where they are, and the Leech Canyon Dam's right here, so you can see there are several areas of a high hazard for that. Then 6 months after the Holy Fire and 18 months after the Rose Fire was a good-sized storm. In 12 hours, it was a little over 4 inches of rainfall, which equated to about a 20-year storm. And then for the 15-minute interval, it was about 0.3 inches, about a quarter inch of rainfall, which equates to about a 2-year storm. And so that the inches per hour peak for the 15-minute interval, and that's the one that the USGS considers a design storm for that type of model, is 1.2 inches per hour, which is very similar to the 1 inch per hour for the design storm over a 15-minute interval. And you can see too is that this is a graph of the rainfall with time, and it was a pretty steady storm. So it wasn't 4 inches in a very short period of time and then it leveled off. It was quite consistent in terms of its rainfall rate. And this is some imagery after the rainfall occurred, and this is just some example images, but you can see the erosion that was scoured into these draws or these side canyons. And then you can see in some of them the actual failure at the top, at the head of the debris flow, and then it came in, and of course with the reduced strength and the bulk unit weight, it eroded and carved into these sides, and that resulted in the volume of debris that came down.
All right, so now looking at the Leech Canyon Dam and the basin behind the dam, in preparation or anticipation of a winter season, after the Holy Fire occurred, the basin was cleared out, which was good practice. But here you can see this photograph after the debris flow. You can see that it's basically filled up. The whole dam basin was filled up, and it overflowed and drained out through the spillway at this bottom of this photograph over here. You can see the heavy erosion that occurred down along this area here. Note that these homes directly below the dam were not damaged, but we'll discuss a bit what happened further down the spillway channel, down the floodway channel. And about a year and a half later or so, this area below the spillway was restored and the repair was completed. Now, we're looking at the dam here, the spillway, and here's another view looking up from the triple box culvert, looking upstream through the, you can see the spillway and the dam back over here. We know that the dam was overwhelmed with debris, and the spillway, and then the erosion debris came down through the triple box culvert, overflowed the street, and flowed down through this leach canyon channel. Looking at this leach canyon channel here, it was designed to be it was intended to have a 200-foot wide easement here, and the county required that this easement be clear of any structures, improvements, fill embankments. Upon review of various historical aerial photographs, you can see that, and also even these photographs here as well, you can see that slowly these homeowners along this side over here had built out into the easement with structures and this large amount of fill that was placed over here too, that constricted the 200-foot wide floodway to only 50 feet in some areas, increasing the velocity, increasing the erosion potential in that area. So we talked about the damages that occurred upstream along the dam, and we're looking now at the resultant damages downstream of that area. And as I say here, the floodway was reduced in cross-sectional area by about 75%. Looking at it from a ground view, you can see here the amount of erosion that occurred below some of these structures, about 15 feet of erosion along the edge of the channel over here. You can see these various walls had collapsed. These structures have been undermined in various locations. And basically, partially, the thing is that the flood control district may not have enforced the land usage of the flood channel as it should have been. This may have partially been preventable, but with these kinds of events, when you have these types of debris flows, it can kind of show the weak spots in the various drainage infrastructure. So.
Just to pull everything together is, there was the 1,600 acres of watershed that was burned in 2017 and 2018, and then 1 year later or less, there was a moderate-sized rainstorm, and that rainstorm resulted in debris flows from that whole watershed area and overwhelmed the dam. Even though the dam was cleared, it damaged a spillway. It left debris in the channel and eroded debris out of the channel. It undermined some properties. And so, some things here is that the modifications of those properties reduced the channel significantly. And if you think about the type of damage that's occurred, it doesn't seem like there were any lost lives or anything. But imagine if the dam was not cleared out, how much damage there could have been. So the dam, accepted a huge amount of sediment, but that filled up relatively quickly, and then there was still a significant amount of sediment that came down the floodway. And as far as lessons learned, even though there's just a moderate storm event, because there was a wildfire before, there was significant damage to the dam, the spillway. Downstream of that, it overwhelmed the triple box culvert and overtopped it. So that wildfire was a major factor in the kind of debris flows and damage that happened. The USGS modeling, it did predict where the debris flows occurred. The volumes maybe were greater than what the model predicted, but it did appear to do a pretty good job of predicting where the debris flows would occur for the design storm.
With regards to additional lesson learned or almost reminders, it's pretty imperative when there are times where you may be anticipating debris flows, for example, after a wildfire or if a large storm is coming, to make sure that you assess and maintain the drainage infrastructure that is there, whether they be spillways, basins, like Taki had mentioned, the Leech Canyon Dam Basin was cleared out shortly before the event. Check the channels in order to limit the damage. You can't really stop the damage, but you can, try to limit the damage to the best of your capacity. Because of these debris flows, the drainage infrastructure isn't typically designed for those. A lot of times it's designed for more runoff and water as opposed to this sediment, cobble, and organic entrained debris flow that occurs. So it's important that you take care of all the infrastructure. And for example, similarly for the floodway easement requirements, make sure that those easements and those floodways are clear, so you can actually use them to what their purpose is. That's something that is very, very imperative to keep these types of events as the damage as minimal as possible.
And one more thing too is about the floodway easements is that the restriction of the floodway channel, it damaged the properties that encroached in the easement, but it also damaged properties downstream because it changed the flow path. It increased the velocity. So some of the properties downstream were affected even if they didn't modify within the drainage easement. So that's important, and that's something that could be avoided. And so that is the end of our presentation.
And also, as Naveed had mentioned, a paper that Taki and I and our father put together regarding good practices for landslide reconnaissance. That paper will be presented in Geo-Extreme in November in Long Beach.
Pavlo and Taki, thank you so much for your presentation. Very enlightening. As we wait for questions, I do want to remind that if you have questions, please put it in the chat box, and Brad will then relay it to me, and I can ask Pavlo and Taki. I don't think there's any questions at the moment. You guys just finished, and so I was very interested. I'm very excited. Obviously, I live on the Gulf Coast. Wildfires are not necessarily something that I see every day, nor do I want to see every day, because we are in hurricane season right now and almost peak hurricane season. But what I did see is a lot of similarity is how we try to control risk between flooding, hurricanes, and wildfires. And so I do have a couple of questions. I see Brad is typing. I'll go ahead and get started. And then if there are questions that follow up, then we'll ask them. So the USGS, I'm a homeowner in this area, right? And so you have the Holy Fire of 2018, and it's pretty bad. I'm a homeowner there. Boy, okay, I dodged the bullet. I didn't get burned down. All right. And then the USGS does their modeling and says you have a 60 to 100% probability that you're gonna see a debris flow or you're gonna see some flooding. And so I'm trying to understand from the homeowner's perspective, how do I reconcile that? Like, it's like, okay, this is coming. What do I do?
Yeah, something that that's a great question. I think it's very applicable to everyone in terms of various types of geo hazards. But typically what we see that's the most effective, we've seen various types of flooding events, and what's been helpful is basically if there's a flooding event, for example, or any type of, you expect some type of erosion to occur and debris flows, typically sandbagging as much as you can. The one thing is to assess the topography of your site. Are you on a higher land or the lower side? Even like what side of the street you are on. We've seen somewhere, the neighbors on they're a little bit higher. The homes they have a driveway that's steeped up maybe 2 or 3 feet higher. The other side of the street, the exact same street, they're right at grade, and those homes get flooded on the side of the grade versus the higher homes. So taking account, almost doing your own engineering, reverse engineering to see if the water is going to come down, where is it going to flow along the street here, and put those as many sandbags as you can to basically minimize and just kind of predict what's going to happen. It's very difficult to predict exactly how much flow is going to come through, but rather be on the safer side, as you can imagine, than possible.
Yeah, it's funny. I do that as well. There's a small creek that runs near our home, not like next door, right? But at least 1,500 feet away. And so I look at the properties next to me and like, okay, they're a little bit higher than me. They're a little bit lower. And I do my own drainage engineering. So staying on the USGS model, right? I understand it's a big picture model. You're looking at regional scale. It's not like geotechnical engineers where we typically hone in on one home or one infrastructure. And there's a couple of things that go into that model, like you talked about: topography, the rainfall intensity, soil properties, and burn severity. So I want to get a picture from you. If you hold the rainfall intensity constant and you start turning the dials of this model to see what is truly affecting the predictions of debris flow, what is really affecting the possibility of a debris flow?
So the main ones are going to be steepness of the slope is a big one, right? Because if it's flat and it's burned, it's not going to have a debris flow. Burn severity is important. I think as long as there's moderate burn severity, you have the more potential for debris flow, because you have ash, you have like the light vegetation was burned. Maybe the trees aren't burned, but if the light vegetation is burned, the brush, that still has a high probability. You can have debris flow from that. So I think those are the two main, major driving factors that we're looking for. And then also, I don't know if that model does that, but certainly looking at whatever is upstream of where you're looking at. So if you're looking at if a debris flow happens upstream, it's obviously going to scour and cause more volume down below. So there's some cumulative effects there, but yeah, that's how I see it.
Okay, so we didn't say anything about geotechnical properties, which, us being Geo-Extreme, if you could give a plug for how the geotechnical properties could be also relevant for any types of prediction.
Yeah, so as far as the soil properties, certainly thickness is really important of the debris, right? If you have the thickness of the debris of the soil on the slope, right? If you have 3 inches of soil, basically exposed rock, you're not going to have much debris flow. As far as the properties, the thing is with the ash layer that deposits, you can get there's not that much infiltration that happens because the ash layer has low permeability. So that the presence of the ash layer can play into, when we talk about geotechnical properties, talk about wet strength or dry strength. That's going to affect the way that the soil can be wetted, is the presence of the ash layer. And then clay versus sand. Sandier materials are easier to erode typically, so that's going to be part of it too. Is do you have more of a sandy material that can get washed out easier, or does it tend to be more of a colluvial clay that really has to be scoured and eroded to actually come down? Those are some of the factors at play.
Sweet. Okay, we have our first question. I'm going to read it out to you. It's from Sean. The debris flow risk model, so I think we're staying on the USGS model here, shows some higher risk channels upstream of lower risk channels. I think we talked about this a little bit. For the lower risk channels, does the study take into account the upstream risk, the cascading risk?
So my understanding of the model, I did not prepare it or was not involved in that, but my understanding is for the hazard, like that last slide that I showed, that was the debris flow hazard, that was simply combining the steepness of the probability of debris flow with the volume of flow. So I noticed that too, is that the upstream portions had a higher hazard. What I think that is the steepness of the slope is much more. So the probability of debris flow at that location is higher than downstream of that, just because it's steeper. So when it comes to the actual model itself, so I think that's what's happening.
Gotcha. All right, we have our next questions from Demian. Did you open the USGS, staying on USGS, GIS data and review the segment data for the segment site-specific data for probability and volume? The data have their reported volumes in low and high values.
Well, I know for the current fires, the USGS has that GIS data where you can look at the incremental data for the model for certain areas. I don't believe for the 2019 slide there was that resource. Okay. As far as the volumes, from what we can tell, the volumes of the debris flows were significantly greater than what the USGS model predicted.
Okay, so USGS underestimated debris flow volumes. Excellent. Well, not excellent, but it's good to know. So a follow-up question from Sean. Who gets the blame, and air quotations there, liability, you could say, for narrowing the channel in the housing district?
So We weren't involved in that portion in terms of the liability, but I would imagine it could be split between various parties, between the flood control district for not enforcing these items here in terms of the blockages, but also the 200-foot wide easement was within those neighbors, those properties along the, I think as you look downstream along the left side where they basically built out there. I mean, that's clearly, I think that's a big factor in terms of the damage that occurred down there. So probably the bigger piece of the pie would be those homeowners who had built out against what was allowed by what was stated in their easements.
Yeah, always a tough question to talk about liability.
Mm-hmm.
Someone's got to be blamed. Okay, so let's keep going. I'm really fascinated. You said flood control like districts, I guess, and we have those as well for levees. The dam that was constructed, it's obviously a dry dam. It's there until it needs to be there. And then you have the drainage infrastructure, which is not necessarily designed for debris. So can you talk to me about what does that infrastructure, in designing it, is there any type of considerations for design, for construction, for operation that is different from what a typical geotechnical engineer thinks of as a dam?
Yeah, certainly a dry dam would be like it's basically a temporary condition where you have that. So in terms of typically with dams, you have a higher groundwater table. You have to worry about liquefaction here, right? In this kind of situation, the groundwater table is quite deep. And so the water that comes down is, of course, temporary. It's more for, it's a debris basin, essentially. Even though they call it a dam, it's more of a debris basin.
Yeah.
So I would imagine it would have different design requirements. I don't think we're aware of I mean, obviously it was built a long time ago, but any requirements as far as it being maintained or upgraded like other dams are in the area.
It just does appear that, maintenance is done. Looking at old aerial photographs, they do try to clear out that basin because it does, all that runoff goes down into Lake Erosional, which we said is like the largest man-made or largest natural freshwater lake in the area. So it does get a good amount of runoff. So controlling that runoff from those canyons is very, very important. So clearing it out is important maintenance, especially since the dam was built 70 years ago.
So the debris volumes were overestimated from the USGS model, maybe indicating that the capacity of that dry dam is not sufficient today or moving into the future. How do you kind of look into the future now and say, okay, this infrastructure is not sufficient, and what do you do about it?
Well, sufficient, it's interesting looking at the performance, and that's why these case histories are helpful, because we have an actual, it's not something that was a finite element model and we think this is what happened. We actually see what happened. And so the debris basin, it took, it's about 4 million cubic yards of material that it can store. In terms of damage, I mean, if there was some damage to the spillway, so you could improve the spillway so it's just not going to erode it, because you may get scouring and that kind of thing. A lot of the damage was really downstream where the areas were modified. The floodway was modified and it was actually constricted. So if you remove that area, it seems like the dam did its job, even that shortly after a fire. Because as time goes on, you go 10 years later, 20 years later, the vegetation regrows and the amount of volume that comes down would be a lot less, So, it went through the ringer in terms of a wildfire and a moderate storm with all that debris, and the homes didn't get washed away, at least the ones that are right downstream of the dam. So I think that was a big win for the dam. The dam should have at its performance.
Yeah, but clearing out the channel of the other improvements that were done, or the modifications that were done, being those structures, those fill embankments that were placed, clearing those out would help restore the capacity of that channel floodway.
Perfect. Well, you did create, you said 4 million cubic yards, right, of debris. Where did that, as someone who's dealt with disposal and geoenvironmental engineering topics, where does all that debris go?
We weren't involved in the removals, but typically there's going to be various landfills you have to place it in. Maybe you could restore it and place it in other areas because it is, I believe, county property. So you could maybe put in other locations if it clears the environmental testing.
Gotcha. Okay. So either ends up at landfills or could be stored for other options if it's not contaminated. Okay.
Right.
Just a reminder for those folks who are listening in, if you have questions, please put in the chat box and we'll get it asked to both Pavlo and Taki from their presentation. We had that discussion of a dry dam. I was going to say, I think it's more of a levee. When we were educated on the difference between levees and dams have constant water behind them at all times versus levees. They're there when the flood comes and then they stay dry. What is, we talked about the future, right? But do you at all pay attention to the severity of rainfall or wildfires and forecasting how that might affect communities like this?
Navi, can you say the first part of your question again?
Yeah, I'm looking at, I tend to think, let's look at climate and future predictions, right? Forecasting how severity is going to get worse with wildfires, the droughts are getting worse, rainfall intensities are getting worse. Is that changing any dynamics in terms of kind of looking into the future?
It should. I mean, that USGS modeling, it is definitely, there's room for refinement. And I'm sure with, AI and better drone capturing capabilities than in 2019, that there's a lot of opportunities to improve the way that the debris flows are predicted after the wildfire. Being able to go through and do LiDAR scans of entire mountainsides, for example, and get high quality aerial imagery, and then be able to process that probably automatically, whether it's through color or whether it's through relief, and then being able to reduce that into a probability of debris flow or to estimate volumes or something. I mean, that could be really powerful and improve the prediction capability of this kind of model.
Yeah, wonderful. And that's kind of a good follow-up question from Sean. What research should we be doing now to improve our predictions of source, occurrence, volume, and flow rate? So maybe we can hone in on that just a little bit more.
Well, certainly the case studies are a big one because, if you can have the data of rainfall, incremental rainfall data, a lot of places will have, daily rainfall data, but you need incremental rainfall data to do this kind of analysis. You need good data on the burn extent and burn severity, obviously topography, that's an obvious one, and then being able to get the data and test the model as it should be with more case studies. I mean, climate matters too because, different areas, you have different types of vegetation. So different roots, different rooting, vegetation and different soil types will definitely affect the way that that the debris flows can happen. And then the other thing too is climate, right? Because you can have changing climate with time. You can also have different areas, and if you're in more of a desert type climate, and your storms tend to be more flash flood types versus a slow rain, so your 15-minute increment may not be the exact predictor. It may be more of a combination type of rainfall parameter, if you will, rather than just a single simple 15-minute interval. What's your rainfall rate? Maybe there could be a composite rainfall parameter or something.
Exactly, and like this case study here, it was a 2-year storm for a 15-minute increment, but you're looking at a 12-hour increment. We're looking at a 20-year storm, so there could be a lot more to assess in terms of the frequency of the storm, the duration of the storm, intensity, like Taki's saying, and that could also correlating that with the amount of debris flow that occurs. If the debris flow occurs all in one time, or if it is, or if the debris flow is more of a time release, so to speak. So, and then, with what Taki was mentioning about the drone data, there's so much data that could be collected in a very specific manner that you could hone on in various areas that are maybe more problematic than other ones.
Yeah. Wonderful. So I'm going to slowly start winding down here. And so I wanted to ask both Taki and Pavlo, is there anything else you might think about or want to add now that we've gone through a couple of questions in your presentation? Any parting words?
Yeah, I think it's we've definitely seen, I think in geotechnical engineering, there's lots of phases of research. And we've seen recently there's a lot more research in terms of wildfire and slope stability, and the whole purpose, right, is to help the community, the civilization, right. And this is something that we're seeing more and more now of these large wildfires and debris flows. So I like the direction that we're going in terms of the geotechnical industry, the geotechnical research community, to evaluate more about this unknown that we are slowly getting more exposed to.
Yeah, and then one last thing is that, there's a lot of technology as far as, going back to the drone thing, just because we're dealing with large areas with wildfires, being able to record different type of infrared data, say after the wildfires, that can give you a better idea of what areas burned. And, for example, for the 2025 fires, the fires earlier this year, there was basically real-time interactive maps of the extent of the fires. I'd imagine that's from satellite data or something, but it was real time, and it was devastating. But you can see the fire getting bigger, on an hourly basis essentially, and being able to have that data is very useful for using for these kinds of purposes.
Yeah.
So more in that direction would be good.
Certainly. Well, Pavlo and Taki, thank you so much for presenting and getting our live stream started for Geo-Extreme 2025. And so my last plug again is for all those who are watching and who will watch, please go register. The conference is going to be a lot of fun. There's going to be a lot of good content, and it's going to be in Long Beach, which is home to a lot of geohazards.
So, with that in mind, I will make another pitch. On Taki and Pavlo's slides, you saw one acronym quite a bit, USGS. And Taki just talked about the wildfire mapping this year and in the past few years. As many of you may know, federal research is not doing too well in this year's budget and in next year's. It is of vital importance to all the tools that we use as a community. You may sit and think to yourself, well, what difference does federal research make for me? I work in a private firm. You probably use this a lot more than you think. In the recent flooding in Texas, USGS stream gauges came into play. The stream gauge program is $2 million a year. I always say that that's like the best $2 million the federal government spends every year. But many, many, many mapping programs, environmental modeling, you can kind of go up and down the list. Federal Highway Administration funds many of the programs that we depend on as a community. It's always a great time to call your legislator and tell them the importance of federal research to your work. And believe me, that's what they want to hear. So that is our other disclaimer for the day. But yes, of course, you should register for and attend Geo-Extreme 2025. And the most important question I've got for Taki and Pavlo, does this mean there might be a sighting of all 4 Chrysovergis family members at one ASCE and GI event?
Very possible.
It's certainly possible, but you'll have to come to find out.
Well, I'm getting paid to be there. So,
well, to everybody on the stream, you got to come to find out. The big question of the conference.
Yeah.
Oh, I like this. This is the suspense that this builds. This is excellent. Taki and Pavlo, great presentation today. Naveed, well done moderating. To those who attended, thanks for being here. And if you liked what you saw, and you probably did because you're here at the end, again, you should click like, subscribe, and get notifications. And yes, we will let you know every time we post something to the YouTube channel. Our next live stream is in 2 days. It's Geostrata Extra for the June-July issue. We kind of pushed it right to the edge of July there. Jorge Macedo from Georgia Tech is going to join us to talk about the future of tailings storage. You don't want to miss that. You can register for that and all of our upcoming live streams from this very groovy summer of live on our Eventbrite page. So you don't want to miss out on any of that. Our producer today was Aurora Flieger, and we will see you in just 48 hours with another Geo-Institute live stream.